All right, so we are talking about reactions of alkenes in this chapter, but a brief review of how do we synthesize alkenes. Remember, when we make an alkene, it is occurring through an elimination reaction. These are all things that we've learned before. So how do they work? Well, if we have our halogen leaving group, we somehow pulled off a beta proton. The beta protons that would make the tri-substituted product. The most stable product would be either in that position or this position. This is a good leaving group. If we wanted to force an E2 reaction, we'd want a strong, bulky base. So that would look like tert butoxide, and we can just put a counter ion on that. We'll do sodium. So sodium tert butoxide. A polar aprotic solvent makes that reaction go faster. We can say acetone for that, maybe. Acetone looks like this. It's polar aprotic. That is going to force that E2 elimination. If we had conditions for an E1 elimination, remember, we wouldn't want that because that would lead to partial SN1 as well. So we would want the E2 to be the major reaction pathway. In this case, since we have a tertiary leaving group, we didn't even need that bulky base. We could have used a small base such as hydroxide or something, because with the leaving group being so sterically hindered, E2 is still going to predominate. And this one down here, though, this is a primary leaving group. And remember, tosylates, how do they react compared to a halogen? The exact same, right? So primary leaving group, that is going to usually, if we have a strong base, strong nucleophile that is not sterically hindered, that's going to be predominantly SN2. So we would need the bulky base in this case. I'll put a different counter ion this time, potassium tert butoxide. Again, we want a polar aprotic solvent. Anytime we're doing a bimolecular reaction, that's going to be the best option. We'll do DMSO. Remember, DMSO is looking like that guy right there. And that is, again, going to work by an E2 reaction mechanism, where that tert butoxide is going to, it's a negative charge, grab that proton, those electrons go there, and the tosylate leaves. What do we have written here? We're going to do an elimination of a halide or a tosylate with a strong, bulky base if we're trying to force this E2 pathway. So strong, bulky base. That is how to synthesize alkenes when we have a really good leaving group on the molecule. What if the leaving group's not good yet? What if we have an alcohol leaving group? More on that right now. Okay, so alcohols to alkene. How do we do that? We can't treat it with a strong base for a variety of reasons. One reason is that OH- isn't a very good leaving group, and also a strong base would just deprotonate the hydrogen of that alcohol, which would make it O-, which makes it an even worse leaving group. So we can't just treat it with a strong base. So how did we learn how to do this? One way is if we protonate that OH to OH2 plus, it's going to be a really good leaving group. And we did that with sulfuric acid. So that protonated that, and then another product over here that's not drawn in is H2O, right? And we have two products, one reactant. How do we make entropy more important, right? Because going to more stuff means more entropy. What we did there is we would heat the reaction, and that would cause it to go at a faster rate if there is more entropy in the products. It would make it more favorable, rather. The rate might not, heating things generally does increase rate as well. But anyway, so that, again, would allow that to happen. And when we think about things, how they work, this would become a good leaving group. It would leave, it would form a secondary carbocation, and that carbocation would actually change. We would get a hydride shift, to a tertiary carbocation, and then we would get the more substituted alkene there. So that's one way to do that. What if we wanted to form this less substituted alkene? Well, this one went by an E1 type mechanism, where we formed that carbocation and then the elimination occurred. But this one, if we wanted to get that alkene, how would we make that happen? Because this is a di-substituted alkene instead of the tri-substituted alkene that we see up there. So what we'd have to notice is that if this alcohol is going to act as a leaving group and leave in an E1 type mechanism, we are going to have no problem getting to this tri-substituted alkene product. But if it undergoes an E2, then it needs a hydrogen that is antiperiplanar to itself. So antiperiplanar, remember, that means on the opposite face. And if we look at the carbon that we would need to remove a hydrogen from to form that more substituted product on this carbon, the only hydrogen that is around is not antiperiplanar to the OH, it's also a dash. So we would have to remove a hydrogen in an E2 reaction that is on the opposite face, so that would look like a wedge on this flat cyclopentane structure. So how can we force an E2 mechanism with this alcohol as our leaving group? So there's a few ways to do that. Often in organic chemistry, there's more than one way to do a reaction. The most straightforward way would be using one of our specialty reagents. And the one that comes to mind is that POCl3 and pyridine. Remember, that formed an oxygen-phosphorus bond, which is a really strong bond, making this into a good leaving group, and then the pyridine acted to pull off that proton and do the elimination. A secondary way that you could also do it is we could turn this into the tosylate, right? We could, one, treat this with tosyl chloride. That would make it a good leaving group. It would make it the OTS. We need a base around too. We'll just put pyridine in there as a good option. And then secondly, we would treat that with a strong, bulky base like potassium terbutoxide and a polar aprotic solvent that would then do an E2 reaction. So again, more than one way to do this. This is a one-step method. This is a two-step method. So maybe this one's a little bit better potentially, but you'd kind of have to figure that out based on what the experiment looked like in the lab. So if we want this alkene, we have to do it by an E2 way. If we want that one, we have to do it by an E1 way. So again, kind of recapping things we've learned about before, we're doing reactions of alkenes in this chapter. This is how we synthesize the alkenes, and this is recapping previous material. Boom.